Lewis structures, lecture number 7. So we're going to expand on this idea of this Lewis dot symbol, where we can take the valence electrons and connect them in terms of these covalent bonds. And we're going to expand them instead of diatomic, which we've done in class. We're going to start talking about more complicated connections. Right? So we're going to refer to these as Lewis structures. We can also talk about them as Lewis formulas, as it says in the text, because they're not really showing three-dimensionality at this point, but we're really talking about how the electrons are connected in these molecules. So the rules to determine Lewis structures are as follows. So we're going to draw a skeletal structure of a compound showing what atoms are bonded to each other, typically putting the most electronegative element in the center. Around that, we will put all the other atoms. We're going to count the total number of valence electrons. If it's negatively charged, we'd add 1 for each negative charge. If it's positively charged, we'd subtract 1 from that number. And then we're going to complete the octet for all atoms except that of hydrogen. Right? So we're going to form bonds between that central atom and those other atoms. That's going to count each bond, remember, as 2 electrons. And then we're going to fill the octet, so make sure that everyone has 8. At that point, we're going to look at that structure and make sure that the total number of valence electrons equal the number of electrons that we're showing. If we have too many electrons shown, we're going to take some of those electrons away that can't exist, and we're going to share multiple pairs for double or triple bonds with this central atom. If we have any leftover electrons, we're not showing enough with all of the valence electrons, with everybody having 8, then we're going to put those back onto the central atom. And we'll talk more about why we do that later. So in this way, we're going to then follow these simple rules. We're going to create these Lewis structures. So let's look at an example. So let's draw the Lewis structure of nitrogen trifluoride, right, NF3. Nitrogen, because it only has one, there's only one of them, plus it's the least electronegative between nitrogen and fluorine. It's going to go in the middle, as we can see here. Right? Around that, we're going to put the fluorines. Right? The total number of valence electrons we have, the nitrogen, because of its place on the periodic table, has 5 valence electrons. Fluorine has 7. We have 3 fluorines, so that's 3 times 7, 21, plus the 5 is 26 valence electrons. So in our Lewis structure, we have to show 26 electrons. Right? So we're going to draw single bonds between the nitrogens and the fluorine, the nitrogen and the multiple fluorines. That gives us 2 times 3 is 6, so we have to show 20 more electrons. Fill the octet for fluorines. That gives us 24 now. The last 2 go on the central atom. So this is the Lewis structure for nitrogen trifluoride. The 3 single bonds plus the 10 lone pairs gives us the 26 electrons. And this is behind me here is the representation of that in 3 dimensions. So we're always going to do that. Take the one that is only 1 or the least electronegative, put it in the center, put the rest of them around it, connect that central atom to each one of those exterior ones with a bond, count the total number of valence electrons, and then distribute those valence electrons around that so that everybody has the octet. If we're showing too many electrons, we take some electrons away, double bond with the central atom, any extra electrons go back on the central atom. So let's look at another example where we look at the Lewis structure for formaldehyde, which is CH2O. Right? This structure can have 2 possible arrangements, right, that follow these rules. We can have the hydrogen bound to the carbon, which is double bound to an oxygen, to a hydrogen, or we can have both hydrogens bound to that carbon, which is then double bound to the oxygen. Right? Which one of these is the preferred structure will be determined by what we call the atom's formal charge, which is the difference between the number of valence electrons from that individual atom when it's by itself minus the electrons that are assigned to it in this structure. So you can see here that in words, the formal charge of an atom is going to be the total number of valence electrons in the free atom minus the total number of non-bonding electrons minus 1/2 of the number of electrons that are being shared or bonded. Right, so we can abbreviate that this formal charge is equal to the valence minus the lone pair minus 1/2 of the shared electrons. So we'll come back to that in a second and apply it back to which one of these up here is the better structure. But in general, some things about formal charges. The sum of the formal charges on the molecule, or on all the atoms, has to equal the charge of that molecule. So if the molecule is uncharged, then the sum of the formal charges must be 0. If it's a -1 charge, then the sum of the formal charges must be -1. Right? We prefer to have, for neutral molecules, the Lewis structure that has no formal charges, or all the formal charges are 0. That's the preferred situation. Right? If we can't get that arrangement, where we have to have some formal charges in our Lewis structure, then smaller numbers, closer to 0, either positive or negative, are preferred over larger numbers. Right? So we want to get as close to 0 formal charges as possible. If we have to have formal charges, a structure dictates that some of them are going to be charged, then the negative charges are going to be on those substances or those atoms which prefer to be electronegative. Right? So the things that want to bring electrons towards them are going to be preferred to have those negative charges, as you would expect from this electrochemical, or this our definition of electronegativity. It's drawing those negative electrons towards it. So if it prefers to do that, it's going to be favorable to have this negative charge. So let's go back to our example here, the formaldehyde. So which one of these two structures is going to be the preferred structure? Right? To answer this, we're going to look at those formal charges, specifically the formal charges of oxygen and carbon. Right? If we look at this first structure, where we have the carbon double bound to the oxygen and then the hydrogen separated, the carbon there, the valence electron, number of valence electrons is 4. In that structure, the number of lone pair electrons, there's 1 lone pair or 2 electrons. Carbon is sharing 6 electrons, so we take 1/2 of that. We get a formal charge of a -1. For the oxygen, again, 6 electrons in the valence, minus the 2 electrons in the lone pair, minus 1/2, it's again sharing 6 electrons, so we get a +1. So we have a -1 and a +1. Still the sum is equal to 0, so it follows the rules. If we look at this other structure over here, we see now that the carbon has the total number of valence still of 4. It has no lone pair electrons, that's 0, minus now it's sharing 8, so its formal charge is 0. We do the same thing for oxygen. The valence electrons is 6, minus now it's sharing 2 pairs, or 4 electrons, minus 1/2 of the shared, which is again 2 sets of electrons, or 4, and we see that its formal charge is 0. So in this case, the favored structure is this one on this side, where the carbon is double bound to the oxygen, and that carbon has 2 hydrogens associated with it. Right? Because it gives us the smallest formal charges, where the formal charges where we have 0. The last thing we have to consider is that it's possible that we can get arrangements or these Lewis structures where we have 2 structures that are equally favored. Right? So if we look at the ozone molecule, right, both of those have, it's impossible for us to draw a correct Lewis structure where we have 0 total formal charges. So we have to have formal charges present in ozone. So one of those oxygens must be positive and one of them must be negative. Right? With the 3 oxygens, those negative electrons, it's going to be on either one side or the other, as shown here. Right? Both of those are equally favored. Right? They follow all the rules. Those are the smallest formal charges possible. The negative one is on the most electronegative, the same atom. So both of them are favored. So these are what we call resonance structures. They're equally favored. And in actuality, the actual structure is some linear combination of those. It's not this Lewis structure, and it's not that Lewis structure. It's actually a combination of both of them. Right? So you can think of those electrons that are being shared are moving back and forth between those two outside oxygens. Right? So when we're drawing these Lewis structures, the first thing we have to do is follow the rules. Most least electronegative one in the center. Outside, make sure the total number of valence electrons is shown. And then we look for the smallest number of formal charges. If we have two equal, then those are going to be resonance structures. And both, or all, I shouldn't say both, all resonance structures should be shown. When we're doing these Lewis structures, we'll find that this goes back to this octet rule. We always start by putting 8 electrons around each atom. We've already seen that some atoms don't obey this octet rule, hydrogen being the prime example. It only wants 2 electrons, so it's not going to obey the octet rule, or guiding principle, as I say. But there's a lot of other cases in which we're not. Right? We can have an incomplete octet. So if we look at this molecule here, BeH2, we only have, in this Lewis structure, or in this structure, 4 total valence electrons. Right? If we only have 4 valence electrons, then there's no way beryllium can have a complete octet. Right? The most it can have around it is 4. So this is an example where we're going to get a molecule that's completely content or stable, not following the octet guiding principle. Right? If we look at boron, Bf3 in this bottom one, here we have 24 electrons. So it is possible, but the most stable, the one with the lowest formal charges, is where boron only has the 3 bonds to it, no lone pairs. Again, that gives us a formal charge of 0, but it's not allowing us to complete this octet guiding principle. So this formal charge idea is going to outweigh this octet guiding principle. Another example, or 2 more examples where we can violate this octet rule, is if we have an odd number. So if we look at the molecule of NO, right, we only have 11 total valence electrons. Because that's an odd number, we're going to see that we're going to end up with an unpaired electron, which means that the most nitrogen you can have is 7. Right? It's not the 8. But if you look at the formal charge here, that gives us, we take the total number of valence electrons, which is 5 for nitrogen, minus the lone pair electrons, which is 3, minus what it's sharing, which is 4. 1/2 of 4 is 2. 3 plus 2 is 5. 5 minus 5 is 0. So this gives us a formal charge of 0 as well. We also have the possibility where we can expand this octet. The central atom itself can accept more than 8 electrons, like in sulfur hexafluoride. Right? Where it's showing 48 electrons, where now if we look at the sulfur in this Lewis structure, it has not 8, but it has 12 electrons around it. Right? Each bond is 2. There are 6 bonds. 2 times 6 is 12. So sulfur can give us a 0 formal charge in this case with having 12 electrons around it. Still fine. Right? And we will see that the time we get these non-zero or this expanded octet is any time where we get the d orbitals involved. So if there's a potential for that atom to have d orbitals, so everything past, say, chlorine, where those d orbitals are available, those molecules can violate this octet rule by having more than 8 electrons. So we get plenty of practice drawing these Lewis structures, both in this next class time, but also as we continue to explore the information that these Lewis structures can give us.